All right, good morning, everybody. This session, PFAS in organics and compost, starting at 11 a.m. and I believe it goes to 12:30. And we have three speakers. I'm going to introduce our first speaker so we can get right into the presentation. Tyler Brown is our senior project manager with Tetra Tech, with over 14 years of experience in remedial design, including groundwater, pump and treat, and slab mitigation and dual phase treatment systems. Tyler was one of the lead engineers for the design and implementation of multiple PFAS treatment systems at the Pease Air Force Base in Portsmouth, Massachusetts. And he now uses his background in remedial process engineering and emerging contaminants to help solve complex project problems for the solid waste industry. Go ahead, Tyler.
Good morning, everyone. Can you hear me in the back? No, it was a little quiet earlier. Try to speak up. So I'm going to talk a little bit about exploring emerging contaminants in organic processing. I am going to talk about something other than PFAS. I know that'll shock a lot of you because you'll hear that acronym 1,000 times in the next 2 days. So we'll try to touch on something else. Talk a little bit about the importance of organics management, and then I'll focus on what PFAS is, 1,4-dioxane. That'll be brief. I know you're going to hear a lot about that. It was nice to see some students walk in the room, so at least I feel like I'm teaching somebody who hasn't heard this 100 times. A brief regulatory update, a life cycle analysis of how these are moving through the environment, an impact on the business, the organics business, a little bit about treatment options. I snuck that in there because that's my background, and then proactive measures and a future outlook. So what is organics management? Organic management includes collecting, processing, and treatment of reuse of organic materials. That's food waste, biosolids, which is kind of a big topic for PFAS, and then forestry materials. Why is it important? A reduction in greenhouse gases, a reduction in disposal, going to a landfill, trying to reduce that waste going to a landfill, especially things that could be beneficially reused. Reduction in leachate generation. These are usually typically quite wet materials going into a landfill, so you can reduce the leachate generation. Improve soil health, with potential application, and stimulating the economy. So what are emerging contaminants? Like I said, we'll move quickly through this, but chemicals that weren't previously detected or weren't able to be detected. In general, PFAS, you're talking about very small concentrations. So you at times prior, you weren't able to figure out what a part per trillion even was at a regulatory standard. So now we're starting to understand what those are and how to look for them. These are contaminants that may pose a risk to human health. There was a little discussion this morning about how PFAS impacts vaccine effectiveness. Somebody with young children, that really sparks my interest in trying to understand how this might be impacting their effective vaccines moving forward. So per and polyfluorinated alkyl substances, what are they? Compounds resistant to heat, oil stains, and greases, released through industrial processing. There's three categories you'll hear about: precursors, short chain and long chain. Precursors, I think the third presentation today is going to talk a little bit about that in composting, in relation to composting. Short chain is anything with 6 or less carbons, long chain with 7 or more. Those have a different impact on how they leach, and there are different reactions within the environment. So it's important to understand the distinction. Persistent and resistant, persistent in the environment and resistant to environmental degradation. That's really why we're all here. They're a pain to deal with, and we've figured that out over time, that they are very difficult to handle. And bioaccumulation. So these compounds bioaccumulate, and as we move through this presentation, you'll see some examples of what that means and why it's so important. Here's some of the things that they're found in. Again, firefighting foams, adhesives, water repellent, clothing, carpeting, and furniture. Dioxane. So this is the other emerging contaminant we'll talk a little bit about. Dioxane is a synthetic industrial that chemical that completely miscible in water. It travels very quickly in water and is difficult to get out. It was historically used as a stabilizer for chlorinated solvents, paints, strippers, and waxes. It's relatively resistant to biodegradation, so you're not going to see that natural breakdown that you would with volatile compounds. Rapid migration due to its miscibility, high likelihood of being in leachate, and we'll see some examples of that as well. And it was used in pet manufacturing and recycling. And here are some things that are found in: pesticides, dyes, greases, antifreeze, etc. Regulations. So we'll talk a little bit about regulations or the lack thereof. The EPA has not moved quickly on this. So you've seen a slow rollout of EPA regulations for PFAS. There is no MCL within the EPA. There was a drinking water health advisory issued of 70 parts per trillion. PFOS and PFOA being the two main focus, but you're seeing as we talk about the states, some others being focused on, were added to the contaminant list. The big document that came out between originally giving this presentation 2 years ago and now is the PFAS roadmap that the EPA issued. And one of the key things for this presentation is the focus on biosolids and a risk assessment of biosolids expected in 2024, which is still a ways out. The focus has largely been on drinking water, groundwater, the things humans are ingesting, and that makes sense. So something like the solid waste industry lags a little bit behind that, and you're seeing that with these regulations. State regulations, I'm not going to go through all of them. I know there are a lot of different states represented at this conference, so I tried to focus New England based. I'm based in New York, where we do have an MCL of 10 parts per trillion of PFOA and PFOS. Other states like Massachusetts have 6 compounds that are regulated. New Hampshire and New Jersey are focused on other ones. They've added in PFNA, PFHXS. Maine, where I lived before New York, actually has a significant focus on soil screening levels. They've had several farms that we'll talk about that have been impacted. So they've focused on soil screening levels for PFOS and PFOA, and among other things, fish tissue, crop specific guidelines, understanding how biosolids are affecting these farms. Don't expect you to read all of this, but it's just an example of the variation between states, and not only a variation of the concentrations, but also of what is regulated. And you're seeing that across the board. States with no regulations, states with just a couple. I still get questions from clients all the time, not understanding what's going on in their state. And I meet with other Tetra Tech employees across the country, and they're just doing completely different things. They're at a completely different phase of this rollout. In New England, we're way ahead of the curve, it feels like. And so trying to guide somebody who's a little bit further behind is an interesting juxtaposition. This is just an example of some soil screening levels, as we talked about in Maine, Connecticut. I know Massachusetts is also requiring sampling for biosolids and things like that. So that you are starting to see these roll out, but you're not seeing a regulatory standard that people have to hit yet. 1,4-dioxane, similarly, no MCL for drinking water, but there is a drinking water equivalent of 1 milligram per liter. There are some industrial soil and air screenings as well as residential. And there was a risk assessment completed in 2020. State regulations, New York was the first to adopt an MCL, 1 part per billion. Other states like California and New Hampshire, they have regulatory or reporting limits. They may have a drinking water notification level. They don't necessarily have a hard MCL for this. So how does this contaminant enter the organics waste stream? We'll talk a little bit about PFAS and then 1,4-dioxane. Pretty simple graphic kind of explaining the cycle, right? You'll hear a lot about PFAS is just moving around and not necessarily being anything being done with it. And what does that mean? So there's 3 main pathways: air, solid waste, and water waste. We'll focus a little bit on the solid waste to start. You have PFAS entering landfills through your products that we talked about, your carpeting, food waste products, and then leaving in a variety of different ways. Now there is PFAS in landfill gas, but it's not a large focus at the moment. Concentrations so far have been shown to be pretty low. So the main focus is your surface water discharges, leachate, groundwater. Leachate leaving a landfill typically cycles back to a wastewater treatment plant, headed to a POTW. If there's no pre-treatment, that PFAS is moving directly to the wastewater treatment plant, where they may or may not be focused on it either. As regulations roll out, they are starting to focus on it, and you're seeing that roll back to the landfill. So landfills and clients that I have are calling me saying, well, they're not regulating leachate. What does that mean? It's like, well, they may not regulate your specific leachate concentrations, but they are going to regulate what they have coming into their wastewater treatment plant as they start to understand more. So that's where the red flags start to get raised. As you move through the wastewater treatment plant, you have the surface water being discharged. If it's not treated, the PFAS is being discharged to the drinking water or aquatic life and then ingested. And then biosolids, which is kind of where we'll move to in the second half of this presentation, is the biosolids are either being surface applied with contaminants within them and then getting into the crops. Those crops are then ingested by us, by wildlife, by livestock, or disposed back to the landfill. And that's where that circular process, you're taking that PFAS, sending it from the landfill to the wastewater treatment plant, and then back again. Landfills are shown to do a pretty good job at sequestering PFAS within them, but it can't keep it all in there. So you end up having this constant cycle through. Dioxane's a similar setup, mainly coming from product manufacturing and product use. Those are then discharged down the drain, recycling, disposal, and that's where we ingest it or have exposure to it at our houses. Generally, that's both the general population and the ecosystem being exposed to dioxane. Some headlines to grab your attention here in the middle. You're seeing a lot of headlines and recently about these forever chemicals, right? That's how the public refers to them because they don't go away and they're everywhere. States like Maine, Alabama, you're seeing it in beef in Michigan. They're starting to look for it. They're starting to understand, and people are starting to become aware of what's going on. And you're seeing a lot of these very eye-catching headlines that when I get sent by my grandmother or my mother, they're quite concerned. They don't know what's going on, and they come to me and they're like, well, you know about this, right? And it's it's fun to try to explain it. So how does this impact contaminants and organics? So a few examples here of how this is impacting the market. Paper mill residuals, have been applied over farmland. You get that beneficial reuse, right? You don't want to send it to the landfill. You want to reuse it. Well, high levels of PFOS were found in all the soil, the surface water, the drinking water, and the milk. And the milk kind of stands out quite a bit because if you look at that level, 938 parts per trillion, and you think about what that health advisory level of 70 parts per trillion, that's an order of magnitude. That's over 10 times higher than what's allowed in your drinking water. That's in my kids' drink cup of milk in the morning. So it's pretty shocking. And you're seeing the headlines, these farms are being shut down because they don't know what to do. It bioaccumulates within those animals. It bioaccumulates in the crops, similar to the understanding you're taught in college or base level about mercury, right? The small fish get eaten by the big fish. The big fish have more mercury than the small fish, right? Don't eat the big fish because there's so much mercury. You're seeing that same bioaccumulation factor in PFAS. Composting facility, I know Todd presenting third will be talking about composting and PFAS levels, so I won't sit here for too long, but it's seen throughout. It's seen in the stormwater, seen in the monitoring wells, seen in the leachate, and in high concentrations. Research conducted in Minnesota indicated that every composting site in the study had at least one sample with PFAS over their health risk level or health-based value. So it is in everything. It's just a matter of how much and what to do with it. Continued application of biosolids over many years has resulted in PFAS contamination. Like I said, with that bioaccumulation factor, even if you're discharging 1 part per trillion over and over and over again, you're building it up. Now, in this particular instance, luckily the drinking water wells weren't impacted, but the site was. Research from Maine has shown all but one biosolid sample exceeded the soil screening levels. So as we start to look for these things, we're starting to understand that they are present. And then sludge samples from plastic manufacturing had concentrations of 20,000 to 138,000 parts per billion of dioxin. There was a study and a notice issued by the EPA that said, you don't need to worry about dioxin in biosolids. It's not a problem. And then almost immediately following it, this study came out and said, I think you might need to worry about it. It is present. Again, that's present in the liquids in that material. It's so miscible. You're not seeing it necessarily adhere to the solids, but you are seeing it in the liquid content of those biosolids. So how does this impact the business? How does this impact the clients? Potential costs for impact of treatment. And we'll talk a little bit about treatment, what that means coming up. But if you need to pre-treat or treat your digestate leaving an anaerobic digester, there's a cost implication for that. Does it make it not feasible to continue these beneficial reuses? Potential limit on the product usage if it's contaminated, your feedstock, what can come into your feedstock, and potential impact on the product value of these biosolids or the compost. Talk a little bit about treatment. PFAS is not destroyed through heating or composting. Again, you're gonna hear a little bit more about composting, I believe, but we're talking about thousands of degrees to break down these compounds. They don't just go away by stirring them up like a soil mixing project for volatiles. You need to do something about it. And we'll touch on that in a couple slides as well. When we first started this, you see a problem, you see, okay, I have something in my water. What do I do about it? You take it out and you put it on something else. Problem solved. Well, problem not necessarily solved when you're talking about traditional techniques, ion exchange, granulated carbon, reverse osmosis. This field is continually evolving, and that's because those initial reactions, that initial treatment isn't always the best thought. When you're talking about treatment of leachate and digestate, that's a lot more difficult. There's a lot of other organic material that creates a challenge with these medias, the carbons and ion exchange medias. I treated groundwater, and you see in that picture, just a little bit of iron can throw these systems off. Imagine what leachate would do to it. So you have to come up with other creative solutions. And that's where the move to destructive technologies comes in. Destructive technologies aim to break the bonds that hold PFAS together. Those are some of the strongest bonds in chemistry, the carbon-fluorine bond. You need to break those bonds and turn it into CO2, water, fluorine ions. You can do that through oxidation or reduction, but ultimately you're trying to break it so you're not just moving it from one thing to the next. And that's the idea. You're not creating that additional waste stream that you have to contend with. It can be utilized for complex waste streams. They don't care what's in the way. This high energy breakdown is going to break down the organic material. Here's some examples of those destructive technologies: sonochemical or ultrasound using sound waves, creating bubbles and breaking the bonds, electrochemical oxidation, plasma treatment, which is what the picture is, which is I just think is stunning. You could stare at that. Probably not supposed to, though. High energy electron beam is something that Tetra Tech and others are working on, using these beams on conveyor systems. As material goes through, you break those bonds and you can use it. It breaks down pharmaceuticals, it breaks down PFOS compounds, it breaks down a variety of different things. Dioxane, again, I've done treatment of dioxane. It is challenging. Advanced oxidation system, bioremediation, synthetic ion exchange media. But again, moving it from one thing to another. And with that complex leachate waste stream, you run into interferences, you run into things that make it more difficult. So how do we minimize emerging contaminants in the organics? First, you need to phase them out, right? These products have largely been phased out in US and Canada. And there's a wonderful phrase there called replacement chemicals. And some of you may know of the replacement chemical Gen X, which is causing just as many problems as PFOS and PFOA did. So when you see replacement chemicals, that might just be code word for another problem, or it could be something that actually helps. So be mindful of that. Many plant-based products are replacing plastic serviceware containing PFOS, but can still be lined with PFOS. And actually, I think it was this morning or yesterday morning, Starbucks is trying to phase out all their PFOS containing products. You're seeing these larger companies want to phase out these things. You go and you get your breakfast sandwich from Starbucks, you're not thinking about PFOS, you're thinking about how hungry you are, but then you're putting that in the garbage, or maybe you're composting it and not thinking you're doing anything wrong. And that's how we end up with these source areas. Reducing single-use plastic, that's always a good thing, but that also helps reduce dioxin concentrations. You're seeing that in cosmetics, you're seeing it in low concentrations. And then minimizing contamination during composting and feedstock, understanding what's coming in and what has higher levels of PFOS. So what are some of the proactive measures you can take? I give this presentation and I sound a little bit like Chicken Little, the sky is falling, shut it down, where you can't do anything anymore. And I don't want that to be the takeaway. That is not the takeaway. Continue to do what you're doing, continue to operate your facilities, but do it in an educated and smart way. As Massachusetts rolls out these regulations for sampling biosolids, do that. Follow your local regulations, understand what is coming into your system and what you have going on so that we can make smarter decisions moving forward. Look upstream, evaluate sources of emerging contaminants. Ban products containing fluorinated chemicals, which Washington State has done. Get involved prior to regulations. And I'll sneak down to talk to your consultant, which is a little self-serving, but get involved. Recently, New York State put out the TOGs for PFAS and they asked for comment. And it's my job to go out there and get involved, comment on what they have, where are the loopholes, where are the things that are missing, where are the things we won't understand, so that when the public looks at it, it's much more digestible, understandable. It helps our clients understand what's going on prior to it happening. You never want to come to your client and be like, hey, tomorrow the regulations are dropping and you can't send that leachate anywhere. They will not be happy with you. So you need to get involved way before that. Education community, seeing students here today educating themselves on what's going on. Hopefully they're educating their parents on what's going on. You need to continue to spread the message and help the community understand, because it can be nerve-wracking. See places like Hoosick Falls and these places where the communities are scared, they don't know what's going on because you have so much information being thrown at them all at once, and you need to make it digestible. And then talk to me. Projecting the future, regulations of organics and other medias. I think they talked about it a little bit this morning. There may be a regulation of biosolids in the state of Massachusetts. There may be regulations throughout other states. So we need to be understanding of that and what will happen with those regulations and how that will impact land spreading of wastes, these beneficial reuses that could be impacted. Further studies and information on emerging contaminants and organics. One of the shocking things is I put this presentation together 2 years ago for this conference. And when I was asked, well, is there any new information? Let's update this. And I did, but it wasn't like when you're talking about drinking water, right? Drinking water every single day, there's a new study, there's a new technology. Biosolids, composting, people are doing the work, colleagues here today are doing the work, but it's lagging behind a little bit. There isn't the huge push for it. So we need to continue to do that, need to take sites and understand what's going on so we can be of assistance for other places. Pre-treatment or treatment could be coming down the line. That one's a big one when you're talking about leachate and digestate, and a challenge that could come down. Education and product information, and ultimately source reduction. Reducing the amount of PFAS will help. Questions?
Very good, Tyler. Thank you. If there are no immediate questions, I think we'll probably move on to our next speaker, and then we'll have a Q&A session with all three speakers at the end. So up next we have, well, Mark, just before you start, I'm supposed to remind everybody that some Massachusetts licensed site professionals and toxic use reduction professionals that you can obtain continuing education credit certificates for attending the conference today and tomorrow, but you have to go to the front desk and get the form initialized by one of the folks at the front desk. So needed to remind you of that. And now we have Mark King, the organics management specialist with the Maine Department of Environmental Protection. Mark is, wow, you're originally from Winthrop, Maine, and you've been with the Maine DEP since 1991, and you hold a BA in biology from the University of Maine and a master's in zoology from Southern Illinois University. Mark works as an environmental specialist in the department's sustainability division, where he serves as the department's compost contact.
Thank you, Deb. Thank you, Tyler. That was an interesting presentation. I actually want to now talk about a central Maine farm that was impacted by PFAS and what we did to kind of correct that. I'm here with my colleague, Mark Hedrick from the Department of Agriculture, Conservation, and Forestry, and we work together on the Maine compost team. So just a little bit of background, the central Maine farm used land applied biosolids from 1990 up until about 2000. And this specific biosolids contained inputs from a paper plate manufacturing company. And as a result had some extremely high levels of PFAS in their materials. The site houses a swine, dairy, and beef operation. And in 2020, the milk was tested, and a routine example of that test found extremely high PFAS levels, especially PFOS. And I'll show you a slide on that in a second. The farmer initially wanted to try depuration, where they basically try to give clean feed for a series of years to try and clean the PFAS out of their system. But due to the age of the animals, it was decided not to try that. And instead they chose to euthanize the herd. Composting was chosen for carcass management, especially during the summer in Maine, because carcasses brought into landfill tend to bloat and smell and create all kinds of odors and leachate issues. And so they felt that composting the material might make it a little bit more palatable for a landfill to take. And so we basically set up the plan to euthanize the animals, compost those animals, test the compost for PFAS compounds, and then decide on what to do with the product. This just shows kind of the farm site itself is located in the upper left area, those two little polygons, the rest of the fields where they actually land applied. And as you can see, all of those fields were fairly high in PFAS. And as a result, most of the feed grown for the animals on the farm was contaminated with PFAS. This just shows you some different testing of the manure and the milk and the dairy cow tissue and some serum. If you look at that first table, the bottom line, the milk tank, that is 32,000 for the PFOS level. And that's parts per trillion. So that was a very, very high number. They were immediately ordered to stop selling their milk product and to put it towards disposal. This is some of the feed. And once again, you can see the numbers and the PFAS are pretty high. Most of this material is what we ended up using as part of our compost amendment for the project. And the average PFAS level was about 82 parts per billion, so it was fairly high. So this is the actual farm itself. I've blocked most of the information as we're trying to protect the privacy of the family, but you can see that the farm is a typical dairy / production farm. The area we chose to compost was on site. It happened to be a place where they put a lot of their mortalities in the past, so that worked out pretty good for us. Our compost plan, I actually worked with the USDA as a subject matter expert for composting, and we developed some livestock guidelines back in 2017. And so we chose to use that same methodology. You create a base to start with, and for the base, we brought in clean shavings from a local hauler, and we mixed it with haylage from the farm to get a 50-50 blend. And that was what we used for the bed and what we also used for cover over the animals. The carcass layer consisted of the animals themselves, and then we covered them with a hot mix of manure and haylage, which is a type of fermented hay. Both were very high in PFAS levels. And then the cap was once again the shavings and the haylage. So we started out first with the swine. The swine were fairly large. A lot of them could not walk because they were so big. So they were the first ones as an animal welfare concern to go down. And we took them down. And as you can see, some of the tests from those animals had an average of about 8.4 parts per billion. And the advisory was 3.7. So these animals were not fit for human consumption. So they immediately went into the pile. And we started out by laying a bed. We used a total mix ration wagon to mix the clean shavings and the haylage. The farmer would not put any manure through it, so we couldn't make a blend of the manure and haylage. But he did put clean feed and haylage together, and also the shavings. Once the bed was laid down, there's Mark doing the raking. We smoothed it out, and this bed was big enough to house all 35 of the hogs. And so the animals were brought into a chute. They were humanely euthanized using a captive bolt system. And then they were brought to the bed and they were laid out to get the best use of the space that we had available. And all were sampled for tissue, manure, and blood serum. Then the mixture that was put on as the cover was the haylage mixture. And then this is actually the manure and haylage. It was wet, dense, but what I found is that it has a lot of biological activity. So when placed on the carcasses, it really kind of sped up the composting process. We actually were able to get them down to bone in about 4 weeks. So it was a really hot, super active material. And so I'm really a big fan of adding that on. This is the final cover being applied. And this is the temperature profile for the swine. And as you can see, about day 25, we started to notice that the temperatures were starting to decline. And usually when the outside temperature and the inside temperature start to get really close, it's time for the pile to be turned. And so we turned it, and that's when we noticed all the degradation down to the bone. But upon turning it, it immediately rebounded and got super hot again. So that's the whole process for compost. You keep the active process optimal, and it keeps on working for you. So then the next thing that we did is we did an excavation of the pile at the end of 8 weeks. And that's pretty much what we had left over. So it really did a good job of taking the soft tissue. Next, we moved on to the dairy cows. Once again, they had some fairly high numbers. They were roughly around 1,100 to 1,500 pounds each. And as you can see, I highlighted the PFAS in the middle there. But you can see that the numbers were once again 50 and above, and the standard was still, in the single numbers, so it was extremely high. We once again laid out beds. This time we laid out 2, and that was enough to accommodate 59 dairy cows. Same setup. They were brought by skid steer, and they were placed by excavator with a thumb. It allows more manipulation to put them exactly where we wanted them, which is always very helpful. And we also hired a very adept contractor. And that is one of the keys. Whenever you're dealing with carcasses, the better capable the contractor, the smoother the operation. If it's someone's first day using a skid steer or a bucket loader, not a good day. The animals were then covered with another good mix of the sawdust shavings and the haylage. And as you can see, this is the final cover being applied. And then we ended up with 2 windrows that we then sampled again. And we sampled, I believe, in 5 or 6 places per windrow. And this just gives you an idea of the temperature performances. And once again, as you can see, we got very high temperatures. We like to see an excess of 131 degrees Fahrenheit, especially if we're dealing with any pathogens. But in this case, we just wanted to deal with good, complete carcass degradation. And we're able to achieve that on both very well. We currently now have 3 windrows going that have 145 beef animals in it that we ended up starting in late November. And we're in the process of testing those this spring. So this is the results. And as you can see, the PFOS levels were fairly high in the finished compost. The one thing you don't see here is we don't have a balanced equation, a mass balance equation. because we put in a lot of weight of animals that were fairly high with PFAS. We also put in a lot of manure and haylage, and the only thing that wasn't contaminated was the clean shavings that went in. So without a proper mass balance equation, it's really hard to understand if there's any degradation at all. I do believe the experts when they say the PFAS can't be broken down, but I also know that composting has a way of kind of doing unique things. So in my mind, the jury's out until I do a study with a good mass balance to be sure. Some of the benefits, though, from the perspective of dealing with a difficult material, is it does tie up nutrients. All the leachable nutrients get bound up into more complex compounds that are very recalcitrant to break down, which is a really exciting thing. It does treat leachate generation and reduces it. So from a landfill standpoint, it takes a juicy, gooey, odorous material and makes it much less so. So it makes it a little bit more easy to handle for the landfills, which I think is really important. It reduces odor and possible vector attraction because there was no smell, and therefore they wouldn't be attractive to birds and other predators. But I do think that the biggest issue from this standpoint is that it makes the materials less bulky and easier to handle and manage. And I think that's the appeal of using this as a way to treat these carcasses. Another thing that's kind of cool is that if you take the average weight, and I went through the literature, it's anywhere from 50 to 70% of the animal's body weight is water. If you look at the amount of weight that we had about 650 pounds per hog times 60% body weight times 35 animals divided by 8 pounds per gallon. That's about 1,700 gallons of leachate that was avoided by being tied up in the compost process. And if you do the same with the dairy cows, that's roughly 7,000 gallons of leachate that would have been released had it gone to landfill. So that was kind of an exciting piece for us as well. It makes them better to handle and less potential for contamination, because as we know, once the leachate goes down through the landfill, it mixes with everything else and becomes something that's really difficult to treat. So some of the future research directions that I see us doing, I'm a big fan of containerized composting. I want to see more facilities use like a roll-off container or something of that nature that's waterproof, and you can put in a hot biological material like horse manure, add your carcasses, cover them, and let them cook in that container. And it doesn't have to be at a specialized spot, but it can allow you to treat them. And then the end disposition can be based upon what the final product tests out at. And I have a project that's happening right now. I'll show you in a second. The other thing that we're looking at in Maine is using hyperaccumulators like fescue and hemp and some of these other plants that pull up a lot of the PFAS that's in the soil, that's in the groundwater. And so that's another possibility to help remediate these sites. But one of the things that I want to start using is all that compost that I generated as part of the carcass study that we did. I'd like to take that to some of the soils that maybe have 1,000 parts per billion of PFAS contamination and blend that in, then grow a crop, a heavy crop like a hyperaccumulator, and see how much we can pull out and possibly remediate these soils back to a usable soil for the farm. So that's another possibility. And this is the project that we have ongoing at our local landfill. And it's pretty cool. It's a 5-yard container. And what you see on the top is a bed of horse manure. But first we put down a layer of wood chips for aeration distribution. This is super hot, about 150 degrees coming out of the stalls, fresh biologically active horse manure. And what you see over on the left, on the bottom, is a bunch of turkeys that were shot, harvested at the same location where we had the high PFAS farm. And we then covered with another layer of finished hot smoking horse manure. And we've been watching it for the last week and a half. And right now the temperature on the outside yesterday morning was 152 and the inside was 160. So that's telling me time for a turn. So I hope to do that in the next couple of days, and we're going to keep following the progress. And the benefit is that we have 6 yards and we know the weight, the bulk density of the horse manure. So, and we know the weight of the birds going in, and we know the concentration. So we can hopefully start to do a mass balance equation on that. And with that, that's it. Thank you.
Mark, thank you. Thank you. So while Mark is changing the slides for our next speaker, which is Mr. Todd Williams, I'll read his short bio to keep everybody entertained. Mr. Williams has a 41-year career in environmental engineering with experience and specific emphasis in the biosolids and residuals management field. Mr. Williams is a recognized composting expert and biosolids management planning expert, having supported the development of dozens of biosolids and residual management master plans in his career. So Todd, you are ready, and give him a hand.
Thank you. I feel like I'm back in school. You know, compost keeps your hair. So just been 41 years I've been doing it. So yeah, it does. You haven't been doing it long enough, Mark. But yeah, it's a pleasure to be here today. I did start composting in about 1981. So that's how long I've been in the business, focusing on biosolids. Of course, back then it's called sludge because it is sludge until it's treated and then it becomes biosolids. So for today, so glad to see everybody here. Charlie's back there. Charlie, raise your hand. I want to embarrass him. Charlie and I've worked together for many years. He still lives here. I actually grew up like in Southborough, so this is kind of coming home. I don't live here now, but we've worked together on many different composting projects over our career. And so this is pretty focused because I've really started working on PFAS and what does composting and other technologies in the biosolid space do. But here I want to talk more a little bit about organics and what's out there. There's not a lot of data out there that I've been able to find, and I'm always open to other people having data that we are learning because we're all in discovery mode. But so with that, let me dive in here a little bit. So what I want to talk about is what does composting do and that we know today. And so here's the outline. It's a complex issue, as you'll hear about over today and tomorrow. There are some regulations. I'm not going to get into a lot of the regulations. You'll hear about that from plenty of other speakers, but I do want to bring us back to what's composting in our vernacular really, and then what's its impact on source segregated organics, and then also some wastewater solids, because I have some data there that probably you haven't seen of, and then some summary thoughts, okay? So I love this slide because this was put together by a colleague of mine who's way smarter than me back in 2014. He's been doing work in remediation of PFAS compounds. And so the key thing here, I don't expect to spend a lot of time on it, but there's all these things called precursors, right? That we don't know how to measure. We can't measure yet in the laboratory, but they're there. So we're not creating PFAS compounds. They're getting transformed to terminal products, right? So it happens a lot of different ways in the soil. It can happen in compost. It can happen all sorts of things. And the main thing here is that this is busy. There's a lot of stuff that's out there that we're still discovering because there's so many of these compounds. And so he did this just on AFFF. That's what this was done. And look at the degradation pathways for AFFF, which, by the way, I don't have a slide that shows this, but AFFF gets a little bit of a bum rap. I think it's a really focused area of concern where it's happened. But AFFF, what's your guess on the percentage of PFAS that's out there is from AFFF? Anybody throw a number out? 3% is right on. Who said that? Smart. So that's it, right? So 97% of these compounds are in other stuff like the carpet that we're walking on and so on and so forth. So, so anyway, it's a real problem in those places where it's been practiced, but it's not something that is the big actor. And what we're dealing with on the organic side, what we're dealing with sludges and wastewater treatment and so forth. So let me back up and talk about, okay, I'm gonna show you some different things of wastewater, which is my background. This study that was done just a few years ago shows that there's variability. They measured PFAS through wastewater treatment plants that had Some had limited or no reduction, but the precursors caused an increase across that wastewater plant. So that, that's goes back to the previous slide. How is that happening? It's because precursors we don't measure. So here's one plant with an influent and an effluent, not a whole lot of difference. This one group, the PFOS compounds went up, but the others stayed about the same. But look at this plant here, okay? It shows up much higher in the effluent. It's variable from plant to plant, depending on how the plant's operated, what types of processes are being employed, and the degree of stabilization that's happening in the processes. So we're learning about that. We at Jacobs we run some plants around the country. And so we looked at one of our plants and we said, well, we know this one, this is a conventional plant, low concentrations of PFAS coming in. These are the concentrations that are coming at the wastewater plant, but we didn't have a significant industrial contribution. And I'm just going to highlight, look at the bar charts here. Here's influent, here's effluent. Here's influent, effluent, influent, effluent. The numbers go up because we get this transformation that happens, and it's largely happening because of aeration. This is published in the literature, and we've seen it at plants we operate. So we get this precursor conversion that happens. So that's important to remember as we get into talking about composting, just give some background there. Here is another plant that we looked at. What about the solids? Because you do get sequestration of some of the PFAS compounds into the solids. And so we saw this one had 100% of the solids were treated through an aerobic digestion process. And we didn't see these compounds initially, detected, but look what happens here. We see this same sort of increase that happens because we're getting more aeration and more degradation. And I believe we're getting more biotransformation that's happening across these digestion systems where the precursors are transforming. So they're there. Now we can measure them, because we're only measuring a couple dozen, like 2 or 3 dozen compounds in the laboratory these days without doing the whole mass spec of every, thing on as a summary, right? So that's what we're seeing out there. You've seen numbers like this. Okay, there's levels, and we know what the main numbers are. State values are all over the map of PFOA, PFOS, and PFBS. Those are the main ones. Here's the screening levels of US EPA. This is actually for I think these are in parts per, these are in parts per billion there. So you see they're protecting groundwater is what we're after here. That's what we're seeing. So I don't want to focus on that. I want to get into our topic area, which is composting. And what do we know there? So the first thing I want to point out, composting, it's a biological process, right? Where we're trying to decompose organic matter under controlled aerobic conditions. And then you can take it one level further, that you're getting into thermophilic temperatures, like what Mark demonstrated in his work, that we're actually doing this controlled. This is different than backyard composting, where maybe you can't control things quite so well. These are massive operations, big scale operations. We want to control these criteria here. And what we're trying to do is do several things. We want to kill pathogens. We want to destroy odor causing compounds. We want to eliminate the pathogenic food source materials, vector attraction, so that flies and vermin are not attracted to the material. And we want to ultimately dry it, like a lot of water came off of that system, as you saw earlier. And ultimately, we're trying to produce a marketable product. We're in a manufacturing business when we're composting organics. Okay, it's not a disposal business. That's a mindset we have to switch. So as a manufacturer, we got to know what's coming out, because we're creating a product that's going to get used, right? So this is a definition that's kind of a modified between the US Composting Council and some other ones. It's a biological process under controlled conditions. Temperatures go up to thermophilic, stabilize the material. The goals to maintain conditions that give us a healthy community of microbes to destroy those pathogens and produce that product. That's a summary paragraph. So those of you that are in college and still studying today, write that down because that's what's said in the textbooks. Okay. This is done by monitoring and manipulating these things: nutrients, temperature, oxygen, aeration, particle size, porosity, structure, moisture, and there's whole topics about that. But this is, what you're doing is all of these inputs, you got microbes that are in there, and what you're doing is getting material coming out, and you have things that come out in the air, you have heat that comes off the process and so forth. So that's in a nutshell what composting is. So what are the materials that we can compost? Pretty much anything organic. Yard waste, pretty common, done when we were first starting this stuff in the 80s, right, Charlie? I mean, nobody was composting their yard waste. It was like burn it stuff, I mean, right? Remember those days? Some of you that are that old, and now there's thousands of yard waste composting operations throughout the US and other places. So leaves, grass, brush, any of that is suitable for that. Source separated organics, pre-consumer and post-consumer food waste. As we see here, pre-consumer food waste is pretty straightforward in that it can be segregated from contaminants, whereas post-consumer is a little trickier because of the contamination problem. We'll talk about that. Manures can be composted, wastewater solids, and clean wood waste. This is some wastewater solids that you see here, some different food waste and so forth. So is Janine in here? I don't see Janine from NEBRA. I'll give her credit on this. This is from NEBRA, which they published this. And this is summary. They just, this is some work that Lascano did, who is from Purdue as a researcher with Dr. Linda Lee, who's doing some excellent work in this area. But they looked at about a bunch of stuff, right? So here's some compost, some manure compost, manure and peat, some mushroom compost, biosolids based, and then you get into some of these dried materials and some other biosolids products. And what's shown here is the main screening limit for PFOA. Okay, so that's the 2.5. And you can see some of these composts, none of them are hitting that number. But then we start to get into some of these numbers that are higher. So that's just showing you some historical measurements that's out there in the literature about, compared to a pretty restrictive screening limit that's out there that Maine has. And others are looking to develop similar limits. So when you look at organics, food waste, and yard waste, what's out there in the literature? There's not a lot. It's not a lot out there. Take a minute on this one. This was some work that Choi did for the Water Environment Research Group. And what's interesting is the first 7 things that you see here are, this is total PFAS concentrations that they're reporting here. These are food waste composts, which allowed food packaging in their mixture, right? So these are post-consumer food waste. And you can see the mix, and here's the compounds. The PFHXA is a pretty big component of it, PFBA. And then of course, PFOA and PFOS show up there. Interestingly, you don't see a big PFOS number in these. You see a PFOA number that shows up. But anyway, that's out there in the literature. Then you look at these last 2, 8 is leaves and grass compost only, which hardly is a blip, right? And then you have 9 as a backyard compost bin, but they left coffee filters in there. And so there was actually probably some contamination from that. So everybody's drinking coffee. I've just made your day. So 10 is leaf compost, again, real low numbers. So that's what's out there in the literature that some have looked at. So the concentrations are quite variable depending on the feedstocks. Now, I went and called Minnesota up because they've done a lot of research in organics, and you guys referenced that, right? Tyler, you mentioned it. And, this is a busy chart. I don't want to expect you to read it, but they have a report that's just been published last year. You can go Google it and get it online. The interesting piece here is they looked at all these different materials by chain length, and then they said, well, we got What about battery, or bakery paper bags, or beverage cups and paper, food paper bags, microwave bags, right? All these different things. Milk bottles that are plastic. So I'm sure you can tell which is the big number, right? Microwave popcorn, probably not a good source for your kids or your grandkids in my case. Paper tableware, which is covered up by me, but that's over there, is the next high number that they reported. And then food wrappers, that we have, that everything comes in. So those are the big hitters that are out there. I asked these folks, where's the data on your compost? And they said, we haven't gathered much on that. We only looked at the leachate running off of some of these sites, or that's being collected, because a lot of these are yard waste and food waste. When I deal with sludges, or, we're capturing all the water and we're taking the water treated. It's not being discharged without getting treated from those compost sites. But their focus is going to be source reduction in Minnesota. So they're looking at how they're going to enact those requirements to get materials like this out of the mix. I asked them, I said, where's the data on the compost from these sites? We don't have any. So I don't know where one of you guys reported that. I didn't see it from when I talked to them just a month or two ago in preparation for this. There might be some old data that's out there, but there's not a lot. There's not a lot. And it varies, as you saw from the previous slide, based on those feedstocks and what people are doing. So let me talk about biosolids, because I actually have some data there that we've collected, because I'm a composter and want to know what's going on. I mean, this is pretty prolific. We've been composting biosolids for several decades, composting wastewater sludges. You're seeing a huge growth in the number of facilities. There's over 4 million tons of dewatered biosolids that's composted annually, making over 10 million cubic yards of product. So it's kind of important to understand, is this a problem or concern that we ought to be looking at, or what can we do about it, right? So here's another study that Lascano did, and I show this. This is kind of interesting because this is a rotary dryer. We're not going to talk about that, but they report in their paper that this is a compost blend. It's really the blend. It's not the compost product. So pretty, it's not that unrevealing in that, oh, if we blend the sludge with a wood product, the PFAS numbers go down because we don't have it in the wood. So that's where you start. And what I'm going to show you some data from some real facilities, full scale, not pilot scale, not laboratory stuff, that shows what the impact is. Okay. This other stuff, just ignore that. That's some other process that they looked at. But the expectation when I started looking at compost was, well, we're going to add bulking agent to it. We'll get a dilution effect. We'll go to the mass balance, right? Can't do a mass balance because of these precursors. And we get this transformation that happens. And so we would expect, hey, if we add a clean bulking agent to those biosolids or those sludges, that the numbers should come down. So we embarked on a study a couple of years ago looking at several different types of sludges and several different facilities. So we measured the sludges going in, we measured the bulking agents, and we measured the compost. Just simply find out what's there, right? So I had the opportunity to look at a plant that has primary treatment with only primary sludge, conventional secondary treatment, which was just composting the waste activated sludge, had a conventional plant where they were doing waste activated sludge only. This was a mix of primary, and waste activated. And then the last one, we digested the material. So it's kind of a range of things that you could do in the wastewater practice to produce your sludges that then you're going to take to compost. We sampled all of these. They were running aerated static pile method of composting. So we're controlling all of those things. We're controlling temperature, we're controlling the moisture, we're controlling the time and the temperature to get PFRP or vector attraction reduction requirements to meet EPA standards. All the standards are being met. And the expectation was that bulking agent would dilute those concentrations before, from the sludge before to the after. That was the expectation going in. So let me just show you some data. So here's PFAS concentrations in the solids. These are typically sludge cakes. So in general, they were not high at any of these facilities because these were not industrially impacted wastewater plants. The fun thing is that PFAS shows in all of them, and it's the higher concentration measured in all of them of those compounds that were measured. And then MIFOSA was the next one. And this one typically is going to degrade to PFAS, I'm told, when you go through the process. But this is what we're talking about, these kind of materials, these solids, okay? Then we looked at the bulking agents, and we had a variety of bulking agents at these facilities too. We had wood chips, ground pallets, ground yard waste, and also some recycled material that's been through the process and then it's brought back around. Pretty typical in compost operations, unless you have so much bulking agent that you want it to go out into the product, you recycle it so you don't have to have as much new. You can use a portion of that. One facility actually used at some point, they had more recycled bulking agent than they needed for new. So they were using 100% of this material as their amendment. And it was pretty telling in that the bulking agent from that facility had the highest numbers because it's grabbing onto that PFAS in their sludge and then holding on to it, and it's just reconcentrating through the process. But I mean, these are not big numbers. I mean, this is a 35, and this is total PFAS concentrations that we measured there of the summary of all those compounds. 25, 5. So these are the different compounds that are measured. So PFAS was 35, PFOS, excuse me, PFHXA and PFBS were the big numbers on that recycle. But the rest of them pretty low, below 5. So some of them not measured at all. So what happened in the compost? Well, here's what we saw. Here we have the primary solids. Here we have the primary with waste activated mixture, the compost of WAS material only, and then this is the digested material in that yellow. And you can see the biggest numbers show up in these two. And that's what we're interested in. The PFOS numbers, the PFHXA, I mean, these are getting up there. So they're a little bit of concern to us for sure. We don't have a standard out there yet. There's some guidance values that Michigan has, and we're starting to push up to these numbers. So we want to keep an eye on that. So, and this is what we're talking about as a product, a screened product that's ready for use. I took that data and put it in a little different presentation here. So here's the sludge, here's the bulking agent, here's the compost. This is comparing PFOA and PFOS. The PFOA is the blue and the PFOS is the purple. So the PFOS is the predominant compound that shows up there. And here's what we see in the sludge. Here's what we see in the bulking agent. And this one, and again, we had the big recycle bulking agent. The other one, this one here didn't even measure, didn't even show up. And then we had over here the compost products. And again, the one that was high is the one that was had the recycle the bulking agent. But there's something else that's in play here. The primary and the primary mix with waste activated solids hasn't gone through aeration like we have aeration in the compost process. But look at this, the waste activated that's gone through active aeration and one that's gone through aeration and digestion, we actually saw a decrease from the sludge numbers into the product. So there's a difference, is all I'm pointing out, depending on how that sludge is processed at the wastewater plant and what you might expect from this small group of data. It's only 4 plants where we gathered this data. And I put a appeal out there in Biocycle last February. Anybody who saw that, we're looking for other places to gather more data so that we can get a more robust data set. And so far, everybody's like, no, I don't want to know. Don't include me in the study. As you notice, I don't have any names up here on purpose because this is really just to find out what can we do with composting process to address this concern. So summary points on the wastewater and then summary points on the overall thing. You know, this is small data set. There are some observations. The PFOS is most common. Primary solids not treated aerobically first appear to be more susceptible to transformation during composting. The aerobically processed solids and anaerobically digested may result in less precursor transformation. Again, we want to have more data to figure out that. We talked about the bulking agent recycling. The point is every plants are different. Know what you got. Do some sampling and testing, even if you have to do it independently to try to, you know, people are concerned. Well, that's not a regulation yet. If I test, do I not test? Well, that's a policy question, right? But, you know, if something changes, you'd like to know, do you have to do something in the future? So where do we go from here? We need to just study some more. And what are the role of these precursors in assessing compost? We need to evaluate the impacts on source segregated organics or the properties of this material on transformation. This is stuff that's happening right now. Testing of the leachability, compost products with uptake. Linda Lee's doing some work on that. There's not too many researchers that are out there that are doing that, but that's kind of the next level. But we need to do some more of this. We need to do some more sampling testing to figure out, based on the process, how much the process might have come to play here in impacting it. So that's my presentation. Glad to take questions.
Oh, thank you very much. We still have everybody here, so I hope you have questions for our three speakers. Anybody in the back or here in the front have questions, please, for our speakers.
I know several years ago there was attempted to do a lot of carcass composting out in Washington State. They wound up abandoning concerns for dead cows, sort of was prevalent at the time. But I don't any testing or concern with your current program.
The question was regarding carcass composting and chronic wasting or mad cow disease, any of those species. And actually, it's been an interesting subject amongst our group that wrote the livestock protocols. Currently, USDA does not allow composting as an option for treating chronic wasting disease or any of the BSE or the TSE different organisms. So we really would not advocate for that until we do further study. So as far as cows and things like that, as long as they don't show signs or symptoms, or we have any concerns they might have these organisms or these folded up proteins, we can go ahead and compost them. So there was a mad cow thing that happened, but it kind of just waned a bit. Thank you.
Mark, is that the same for the avian bird flu? Because again,
Nope.
there's breakouts on that.
Yeah, no, I just came back from Maryland. I was down there with a layer house that had the avian outbreak, and that protocol is still standard. We basically compost for 2 14-day cycles, and then the material is released for distribution. So that is definitely good.
You're up, Gretchen.
Sure, thank you. This is also for
Oh, wow. Hot seat.
Sure. Okay. So you had this came up before as well. The idea of the residuals from the paper mills having high PFAS levels. My question is why? What about the paper mills? Why is that a part of the process? Can you explain that a little?
Sure.
Thank you.
In the case of the paper manufacturing process, the solvents and chemicals that they use contain a lot of the PFAS materials. In the case of the sludge that I talked about that had been used on the farm in my presentation, that is actually from the making of paper plates. It's a membrane layer they put in it to make them waterproof. And that is the PFAS material. It's also found in certain, I'm not going to say all, but certain compostable items as well have that layer.
So that was only paper mill sludge, right? That was not biosolids that was on those fields? I was curious.
Yes. Those fields were all biosolids. There had been, and I'd have to go back and look at the records, but paper mill sludge had been spread on those fields, but only a very short time. The majority was biosolids from one specific plant.
So it's not in making of paper, it's in making of other products in the paper.
Right. Usually these material, and I'm not a PFAS expert by any means, but usually it's made to make them waterproof or to shed water.
Yeah.
So it's like in Gore-Tex, things like that. So yes.
Two questions. Number one, I like your idea of the hyper accumulator. I think your idea is to grow plants to uptake PFAS from soil, right?
Yes.
So how do you dispose the plants?
That's a really great
That's
question.
the first question. Second question is how do you dispose the final compost?
Okay, so the idea with the compost for all of the carcass management that we've done is basically it's a fairly high number still. So we have one of two choices. The first choice I'm still working with the farm on is they have several fields that are much higher than the compost itself. And my thought was to use that compost to remediate those fields, spread it, till it in, and then grow a hyper accumulator on that site. We could use fescue. There also is corn crops tend to pull most of the PFAS into their shoots and leaves, but the kernels themselves, the cobs tend to not concentrate as much. So this same farm has a device that creates what's called snaplage, which means it goes through and it harvests the ears from the corn stalks. So we could use that as well and then take those corn stalks, compost those, and then the final disposition, depending upon the PFAS level and the corn would be to take it to landfill. But the idea is that eventually we should be able to pull these materials out and remediate the fields. That's kind of the hope of the research.
Thank you, guys. Just on top of that, there's a great study USM did on spinach, using spinach as uptaking lead in soils in Portland, if anyone wants to look in that. This question's for Todd. Did you have you looked at all in food waste digestate from anaerobic digesters using manure and food waste as the feedstocks?
Haven't seen any data on that. And we haven't done any testing on that. We're well aware of, using that technology. There's a lot of interest in that nationally, as well as New England, out in the West Coast, where people are looking at that. Haven't seen a lot of data in that yet. Do you have some?
I do not yet.
But I think the idea that anaerobic digestion could be something that does some impact on that, on whether it biotransforms, I don't know that we know yet. That's what we gotta find out. Yeah.
Todd, this is a follow-up for you as well. My name is Sheila Conley, and
Hi,
I've been
Sheila.
land applying biosolids for the last 30 years.
Right.
And I really hate that we have a 2-day conference on PFAS. I really wish we were having a conference on the beneficial use of biosolids.
Right.
And that balance of, risk and benefit. And that seems to be lost in this whole conversation when we look at all the good things that biosolids do. So my question for you as a peer in the industry, do you have hope? Because I don't.
Yeah, I do have hope. And I'm glad you brought that up, because there are such great benefits of compost, as Sheila pointed out. You're changing the cation exchange capacity and the absorptive capacity of the soil that you put it into, and the organic content that, and Charlie and I had the opportunity to work with Dr. Epstein, who did most of the research back in the USDA, where we looked at, uptake of metals from compost amended soils was way less than without it in some cases. So there's got to be some benefit that we're going to see when the researchers gather the data, that we're not going to see the uptakes with the composted material, I don't think, as we will with, for example, just digested sludges and that are biosolids still. I think that compost has a unique capability to not totally remediate, but I don't think we're going to see the problems of uptake that we see with other processed materials. That's just my hunch, but we don't have the data yet to see it because it's so hard. But why are there 300, some composting operations out there for biosolids? Because it's a good solution. And the product has tremendous value. You can go out and look at the soils for salmon. If you want to Google that, they have the benefits of compost up there to preserve the water bodies out in Seattle area are renowned in terms of how much it improves and prevents runoff and prevents problems that kill fish, basically. And so we have some great benefits there. So I don't know, where it's headed, Sheila, and I'm glad you brought it up, that we do have hope in it because I mean, I can tell you right now, I'm working on half a dozen different biosolids composting projects in North America today because people still see it as a value. Yeah. Yeah. Yeah.
A question for either of you. Do you see any sign under the various conditions you were composting of mineralization of the PFAS rather than just moving it around from one PFAS to another PFAS or to another media?
I'm not the expert in that area. I'd have to talk to like James Hatton and he would give me an education that would go over my head in a minute, but I don't think you're seeing the mineralization so much. You're seeing a transformation, but it's going to terminal products is what you're getting it to. Charlie.
So in the reduction with the aerated process where you saw the reduction of PFAS, I mean, it's pretty fascinating because what potential could even be the mechanism. And I wonder if part of those studies we should test the air off the surface if we're getting a little liquid vapor transfer because you have so much vapor being driven off in the aerated process. You get the endless steam that comes off of the aeration beds or whatever. So I'm just curious if there's any thought to that.
Well, there's thought to that question, Charlie, and I think when those standards for measuring off of the air are better defined for that might be something we looked at. But I think what's happening, if you go back to this slide, is that you got the primary and the primary mixed with waste activated hasn't gone through aeration yet. So those precursors haven't been transformed. Whereas in these other ones, the precursors have already been transformed in the activated sludge process. So now we're getting the dilution effect in composting is predominating over continuing precursor transformation during composting. That's my hunch.
Yeah, just a comment. New York DEC has done some studies on biosolid composting already. So that is a study from 9 facilities. After composting, there's increased concentration of short chain PFAS in the leachate.
Are you from there?
I'm from Albany, New York.
Yeah.
Yeah. So I will present these studies tomorrow in my
good.
session. Yeah.
Which session?
It is called Biosolid something. Yeah. Yana Liang from University at Albany,
Yeah,
SUNY.
that's great. That's what we need to see. And it'll be interesting because we can share that data and figure out a little bit of what's happening.
Yeah, for sure.
Just the thought of, the air escaping from the composting process. I wonder if the PFAS might get, collected in the biofilter if you're doing an aerated static.
Kyle,
Yep. Yep.
I
And
would guess-
we've probably not tested that filter.
we haven't. So the question is, the air that comes off the process and aerated static pile, if you run negative aeration, you can treat it through biofilters or some other mechanism. What's going to happen is that may be captured in the, if it's there, it may be captured in the biofilter media. I think a lot of it's going to stay with the solids though. It wants to stay with the solids.
Hi, in your definition of compost, do you reference the thermophilic temperatures that are reached in that process in a digester, for instance? But in an on-farm digester, they don't reach those temperatures. They only go to mesophilic. So I'm wondering whether or not that is, it doesn't sound like you've done research based on the question from the back, but I'm wondering, does the temperature make a difference in this?
Does the temperature make a difference? Don't know the answer to that for PFAS, but the temperature will make a difference in terms of how fast it degrades and how fast it goes through the process. Clearly, right? So, yeah, I like to point that out because of the thermophilic temperatures are needed for the pathogen destruction. That's the real goal of what we're trying to do here. Would you say, Mark? Absolutely. Okay.
Any last questions before we wrap? Please, Mark.
Sure. It's for you, sir. Okay.
So my question is in regards to the precursors. You've got me thinking, and I'm really interested in that now. Do you see that same effect for anaerobic digestion or just aerated?
Yeah, I think I think the question is are you going to get a precursor transformation during digestion as well? Yes, I think you will see some. We've got limited data there. I haven't seen digestion really make as big of an impact in terms of reducing it compared to some of these other things. So this is what we're learning. What's the impact of these two different pathways? You put them together now, I think that's where you see those other numbers drop down, was you got aeration followed by anaerobic digestion, and we're seeing a decrease during composting. So you put them together, you've already got that precursor transformation that's probably happened.
We could continue this
Yep.
conversation all day and tomorrow.
And we
There's a
will.
lot of other very good presentations that the conference has pulled together.
Yes.
Tyler, I don't know if you had any last comments or, okay. Thank you. Thank you, everyone.